This chapter we're going to talk about complex numbers. In this first section, we're going to talk about the standard form. Most of this should be reviewed from Algebra 2, so make sure you just have it all down and remember how to handle these things. The reason we need imaginary and complex numbers is because sometimes our answers just aren't going to work out to be real. For example, if we have this equation here and we want to solve this, then we have x squared equals negative 4. Well, there's no number that you can square and get a negative answer in the real plane, so we're going to have an imaginary. We know that our x is equal to plus or minus the square root of negative 4, which means it's plus or minus 2i. This is an imaginary number, the number with the I on it. So we have imaginary numbers like this, and we also have complex numbers. It's a little bit different than just plain imaginary numbers because complex numbers look like this, where we have a real part, A, and an imaginary part, B. So A is our real part and B is our imaginary part. We know, or we should remember, that I is equal to the square root of negative 1. That's how we got our I here, which means that I squared is equal to negative 1. I cubed is the same thing as I squared times I, so that makes it negative I. And I to the fourth is the same thing as I squared times I squared, which makes it 1. Now, knowing all this here, we can calculate out some different values of I. No matter what power we have up to I, we can use our exponent rules to be able to simplify some things for those powers. Even if they're really big, we can use our power rules to be able to do that. We just need to remember that if you have a power raised to a power, that's multiplying them, and if you have two things with the same base that are multiplied together, then we can add those exponents. So for example, if we have I to the 39th power, we want to simplify that down. Well, we take our 39, and since I to the fourth is equal to 1, we can divide that by 4. We get 9 with a remainder of 3. So that's I to the 4 times 9 plus 3. So that's the same thing as I to the 4th to the 9th power times I to the 3rd power, which this is just 1. So 1 to the 9th equals 1. And so we're left with I cubed, which we know is negative I. Okay, so we start out by dividing by 4 and then use our exponent rules to simplify it out so we can get down to these positive or negative 1, positive or negative I. Every single power of the imaginary number, is going to give us either plus or minus 1 or plus or minus I. Let's try one more just to make sure we've got it. I to the 86th power. Well, we take that and we say 86 divided by 4, and we get 21 with a remainder of 2. So that means we have I to the 4 times 21 plus 2. So that's I to the 4th to the 21st times I squared, which is just I squared or negative 1. So that should be review. Hopefully we'll remember that. Make sure you've read through this section because there's a lot of that stuff that we'll cover there. Adding, subtracting, multiplying, and dividing is similar idea to binomials. When we are adding those, just you have to remember to add and subtract like terms. With multiplying, you're going to FOIL those out. So for example, if we have these two complex numbers, 7 minus 9i times 12 minus 3i, you can FOIL that out just like we did with binomials, or if you recall, I've showed you another way where we can multiply just like we do with numbers, where we set it up like this. We multiply this part to here, so that gives us positive 27i squared, and then minus 21i, and here we have minus 108i and 84, and then we add that all together. 84 minus 129i plus 27i squared, except what do we know about this I squared? I squared is just -1, so we can erase that and change the sign there. So then we combine it all together and we get 57 minus 129i. Your answer should always end up being a complex number with a real part, here it's 57, and an imaginary part, here it's -129. Now, division is a little bit different. When we did binomials and we did polynomials, we did long division so we could simplify things out. This is more like with square roots. When we have complex numbers divided, there's a formula in your book on page 342 that gives you this big long formula, but there's really no need to memorize a formula. What you need to do is you're going to have to rationalize the denominator. We don't want imaginaries in the denominator, just like we don't want the radicals in the denominator. So with radicals, we just multiply by the same one, so it would square it and it would go away. But with complex numbers, what we need is the complex conjugate. Okay, a complex conjugate, if we have an imaginary number, it's often called z, a plus bi, then its conjugate, which we put a bar over the top like this, is a minus bi. What that does is just changes the sign of the imaginary part. Now, why would we multiply by the conjugate? Well, that gets rid of the imaginary part, because if you FOIL those out, the part with the plain imaginary is going to subtract away and go away. So when we're doing this, we need to rationalize the denominator by multiplying by its complex conjugate. And remember, in order to not change it, we have to multiply by 1 in disguise. So this is our 1, so that it looks right, so that we end up with just a plain number on the bottom. So we FOIL this out. On the top, we get 16 plus 24i plus 4i minus 6, because we've got 2i times 3i, which gives us 6i squared, and I squared is -1, over, and then on the bottom we end up with 4 plus 9, because this minus 6i and plus 6i, those middle parts, go away. So our answer will be 10 plus 28i over 13, or we can split that out. Remember, when you have just one thing in the bottom, you can split it up. If you have these two, you cannot split that, but if it's just one thing in the bottom, you can split that up. So we have a real part of 10/13 and an imaginary part of 28/13. So this is rationalizing the denominator. You multiply by the conjugate so that we can get rid of the imaginary parts in the bottom. Like I said, there's a big formula in your book for this, but no reason to even memorize that. Just know that you have to multiply by the conjugate. You don't want imaginaries in the bottom, just like you didn't want them for radicals. All right. Let's see. We'll talk about conjugates some more in a minute. Let's try solving for x. What if we have equations that have imaginary parts in them? Well, the thing you need to remember is the I is not a variable. It's a number, the square root of -1. So you just need to treat it as a number and make sure that you are keeping it where it is right then. So what we need is, right now we want to solve for x. So we get all our x's on one side. It's basic algebra. And all our plain numbers on the other side. Now we've got an x in both of these, so we factor that out. So we end up with x equals 2 minus 8i over 5 minus 3i. We just said we don't want to have imaginaries in the bottom, so we multiply by our conjugate. And we end up with 10 plus 6i minus 40i plus 24 over 25 plus 9. So we get 34 minus 34i all over 34, which is the same thing as 1 minus I. So our x value is 1 minus I. If we plug that in there, 5 times 1 minus I plus 8i equals, a little question mark there, 3 times 1 minus I plus 2. So we've got 5 minus 5i plus 8i. So 5 plus 3i on this side. Do we get that on the other side? Well, we've got 3i minus 3i squared plus 2. So we know that 3i squared is the same thing as positive, is changing the sign there. So we'll have positive 3. So that gives us 5 plus 3i, and it checks out perfectly. So x is 1 minus I. The other time you're going to solve these and you're going to end up with complex numbers is if you have to use a quadratic formula. Sometimes that happens. Let's say we have this polynomial and we want to solve it. We know that x equals opposite b plus or minus the square root of b squared minus 4ac all over 2a. So that gives us negative 3 plus or minus the square root of 9 minus 144 all over 4, which is negative 3 plus or minus the square root of negative 135 over 4. And simplify that out, we get negative 3 plus or minus 3i times the square root of 45, 15, I got it wrong in my notes here, I know. 9 times 45 is 5, carry my 4, 36. Nope, that's not right. 15 maybe. 9 times 15. Yep, that sounds right. Yep, 135. So 9 times 15. So pull that out over 4. And notice that you have both complex conjugates, the plus one and the minus one. Now, conjugates are often useful. There's some theorems in your book about them. We're going to do some examples to show the theorems, but we are not going to prove those. That'll be for later stuff to do. So if we have, let's say, z is 2 plus 4i, and let's have w, which is 9 minus 3i. Well, first let's get our conjugates here. The conjugate for z is 2 minus 4i, and the conjugate for w is 9 plus 3i. Remember, you just change the sign on the imaginaries. Well, the first theorem tells you when we multiply our conjugates together, and we'll do this just by example, not by proof, that you always get a real number. If you multiply a number in its conjugate, you get a real number. That's what we were doing when we were rationalizing the denominator. We wanted a real number in the bottom, so we multiplied by its conjugate. The next theorem tells us that if we add our conjugates together, it's the same thing. We get a real number. So if you multiply conjugates or if you add them, you end up with a real number, always. If you have two complex numbers that you add together and then you take its conjugate, so we take z plus w, and then we take the conjugate of that, and we end up with 11 plus I, take the conjugate of that, and we have 11 minus I. If you compare that to when you took the conjugate first and then added it, so we have 2 minus 4i plus 9 plus 3i, you see that they're the same thing. So whether you add it and then take the conjugate, or take the conjugate and then add it, either way you end up with the same thing. Same thing works for multiplication. If we have z times w and then take the conjugate, we have 2 plus 4i times 9 minus 3i, and then we'll take the conjugate of that, and we end up with 30 plus 30i if you multiply this all out. And if we took the conjugates and then multiplied them, you still end up with 30 plus 30i. I assume you can FOIL that out and combine like terms. So adding and subtracting, you can either do it first, or adding and multiplying, you can either do it first and then take the conjugates, or take the conjugates and then do it. Remember, these are examples, not proofs, so you need to make sure you understand why this works. When you have complex numbers, it makes our factoring abilities work a little better. For example, if we have this one here, we can factor this. You just have to remember that I squared is -1, so that's going to, we still want what multiplies to give us -2 and adds to give us a -3i. So here, -2i times -i, well, I squared is -1, so negative times negative times negative, we're going to end up with this negative here. So you have to pay more attention to the signs with your imaginaries when you're factoring. So try this one on your own. Pause the video and make sure you can factor this, and then start it back and we'll check it. So you get x plus 6i times x plus 4i. So you want to multiply to be -24 and add to be 10i. So 6i times 4i, that's 24i squared, which is -24, and then it adds to be the 10i. Now the other thing is with squares. Remember we did difference of squares and we saw how easily that factored? Well, now we can do sum of squares also. We just take the square root of both of them, but we've got this imaginary part. Because now we have square root of 7 times the square root of 7, that's just 7. But we have I times I was I squared, which gives us this to get rid of the negative sign. So there's lots of things that we know how to do with imaginaries. Hopefully most all of this was a review. It should be. Make sure you've read through section 7.1 in your book and have gone over it enough that you're ready for us to tackle some problems in class.